Alright, another draft physics video presentation. I did receive a couple more snarky kind of comments from some anonymous coward type person who sends by email, which is fine, whatever. If light doesn't act like a wave, so again, this act like is not the point. Okay, it's not the point of physics to say, what does it look like? Does it look like a platypus or a rhinoceros? Science isn't like looking at the clouds and going, what does it look like? You're just not doing this act like or look like. It just doesn't mean anything, frankly, because lots of things can do something that's similar, and because the thing it's doing is so simple, like a frequency, you don't say everything with a frequency has to be a wave, okay? Because a wave can have a frequency, a consistent frequency. It doesn't mean that everything that has a frequency is now, we're going to call it some sort of wave or some subdivision of wave. So if Richard Feynman was still alive and he had a YouTube channel, I mean, he's overtly said in his lectures, it's not a wave, I wish they didn't teach it's a wave, it's not a wave. He's overtly said it. Now, would you write this crap to him? Again, I'm arguing that the word frequency isn't anything that you have to tie to wave theory. Lots and lots of stuff in the world right now has a frequency. Old Faithful has a frequency. Nobody's going to call it a wave. It's a mechanical thing. Water rises in the geyser. It takes time for it to heat, blah, 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 and that it's a function. No one's going to say Old Faithful is waving water, right? So frequency shouldn't be some exclusive property that only waves have. Okay. Can you explain the results of these experiments in these videos, these garbage videos with microwave ovens? Microwaves aren't any different than all the rest of the photons. Straight line theory works perfectly fine. It's rays of energy, okay? They bounce at certain angles. I'm sure there's nothing magical that you can derive out of it. Nothing. Alright, but I would argue there is some interesting facts that are revealed by microwave ovens, like the door, for example, that's keeping you from getting microwaved, and the fact that it has holes in it. And why does that work? Why does just sticking some stupid holes in a microwave oven door make you immune to being cooked by the microwaves? So that might be worth talking about. Well, I'll read the second comment first. Do the gravity bit first, I suppose. Gary, according to your theory of gravity, an object experiences more radiation force from the side it is not shielded from. Well, it's not about shielded, it's about how close you are, to something that's absorbing energy. That's the simple truth. Absorbing energy that was heading for you. So in that sense, yes, it's shielding. Okay, it's absorbing energy. Then, for example, if an object, so I already did this inside thing, but I'll do it again. Okay, if an object is inside the Earth, which is kind of a hard place to get, let's understand, to get inside the Earth, you're going to have to make some kind of very high pressure sustaining vessel to be able to go inside the Earth. The deeper you go, the more the Earth pushes back. Okay, so the Earth is now carrying that momentum it's absorbing. So the momentum is still kind of getting to you, right? Because the Earth is carrying it. The particles of Earth are moving towards you. As you go down, they're moving towards you, kind of taking the place of the force of gravity. It would experience less force, technically. Now, if it can overcome the force that now the matter has, if it can overcome that, if you can create your special super vessel that can, withstand these insane pressures, right? And the only way to sustain them usually is to pressurize the vessel you're in. Let's understand that. Okay, because it's being shielded on both sides. It's always being shielded to some extent, okay, just by the mechanics of your feet sinking a trillionth of a millimeter into the soil. You're cheating what is an approximation argument using for point sources. So The idea is that yes, when they're big objects and you can put them in certain places like the Earth and the Moon, it really is much simpler mathematics because you don't have to worry about all of this, like going into the Earth where you're transferring energy that's going in one direction into energy that can go in another direction. Right? I mean, the downward pressure of gravity is going to create a bunch of pressure that wants to squeeze you. So it's been converted, it's been changed in its direction. So you really can't apply the same explicit mathematics when you're inside the point source. Again, I'm not violating any rule that regular physics doesn't concede. You can't go inside a light bulb and then talk about where's the inverse square law. Well, yeah, inside the light bulb it's not going to be the inverse square law. It's going to be some other law. You can explain this apparent contradiction of your inverse square law, of the inverse square law. So it's not a contradiction. You should say apparent violation, but anyway. I think snarkier than it needs to be, but whatever. So I guess we'll go to the drawing board and do the gravity thing. It's true. I mean, I'm saying that yes, theoretically, you're not going to feel the same kind. Your force isn't going to be in the same form. Okay, inside a material body full of, millions and billions and trillions of sources. I mean, each one of the, the whole point is gravity is being created by electrons and protons absorbing momentum. So every single one of them is essentially a point source. So it's like calculating gravity in the celestial bodies. That's what they have to use supercomputers for, because it's so complicated. If you want to try to do a gravitational equation of one star in a galaxy, it's insanely complicated because they're interfering with each other all over the place, and every millisecond it's changing. The gravitational profile. Alright, yeah, so we'll go to the drawing board. I guess I'll pause to get the camera in the right position. Yeah, did I do that well? I should do things where I'm holding something and it disappears out of my hand or something. But anyway, where was I? Okay, gravity. So, obviously, gravity is kind of simple when you have objects that are, well, that's kind of disappointing. Yeah. Alright, down here is where we're drawing. Okay, you have objects that are independent, and so now you can do clear calculations between distance between objects. And really, if you want to be technical about it, you're doing a distance calculation between every little tiny bit inside the Earth or inside the Moon or whatever you're measuring. But frankly, you can approximate because you can know certain truths are generally true, that this half of the Earth is just as massive as this half, and so these two can just cancel out and blah blah blah. So you can make it a lot simpler by doing that. But the truth is that the atoms, the tiniest things in the material universe, are the only things that are moving because of gravity. You're not moving in gravity. Your electrons and protons are moving in the gravity. They're the thing being affected, they're the thing doing the moving. And that's why you don't feel it, is because they're moving, all of them, rather consistently. Right? So we've already had this argument, but the whole reason why gravity isn't recognized properly as a force is because it doesn't hit you like a frying pan. It doesn't, it's the movement is spread over your material substance. Your sun, so to speak. If you were a galaxy, it's moving all of your suns together, so none of your suns can see the movement because there's no disruption. Everybody gets pulled the same way or pushed the same way. It's all the same. And that's like really important. I mean, it's something never taught, I never even heard it mentioned by somebody else, and it's so important to understanding why they made such a mess out of this, is because it's a force that is causing a dramatic effect, and it has no effect that you can see. You can't see the effect because the effect is so even. Alright, so I still have that. What is that? Okay, that was the moon or something. Okay, never mind, we don't need that. So now you're going to go plowing inside of the point source, right? So the idea is the gravity, you can, when you do the approximating, you approximate from a center and just understand that all these radials will be the same length, and so you can do a lot of, this compensates for that, that compensates for this, blah 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 blah. But when you go inside of a point source, okay, then it's not a point source anymore. It's a different source, right? So now if I go inside the Earth, I'm essentially making two new gravitational bodies out of the Earth, okay? I'm making this one and this one between me, right? And there's also this one and this one. Now, for the sake of argument, we can cancel those out because we'll say those effects are all going to be equalized out. But the same thing has technically happened that's happening this way. And so now I'm putting myself between two different sources of gravity that are opposite each other in terms of their influence. One is saying go this way, one is saying go that way. Oh, that's unfortunate. Yeah. See, this is where all that entanglement thing would be really cool if we could just, hey, I need my chalk back. I could just make it fly back into my hand with my special magical powers. But it didn't work that way. All right. So now the inverse square law is going to be based on recognizing this center of gravity and this center of gravity. We have new point sources, and now we're going to measure it this way and blah 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 blah. But the net fact is that I've changed how much matter, okay, is affecting me. And this one's still a lot more on this side, let's say, because I didn't go all the way to the center. But if I did, I guess we should do that drawing, because that's what you're sort of implying. And it really just depends on, so if I go into the center, then you're talking about an idea of being in between two little half Earths, little quarter-size Earths. And so now you're between two Earths, and you're going to measure your gravity, which is going to be 0, because the two are compensating for each other. But the fact is that this system has less diameter in it here and less diameter here than the original diameter, which was like this. So you could theoretically argue, okay, that it's the diameter, it's the number of bits between you and free space that are going to decide how much force got blocked. So you can theoretically say that, well, less force has to be blocked because this diameter is much smaller, and now these two diameters are working against each other. So I had to be blocking, I would be blocked by more gravity. I mean, less of the force has to be used. But again, the point is the force is being used while it's absorbing force. So when it moves an electron and it moves it into you, like you're sitting here, and that electron hits you, the point is you are getting hit by that force, right? The delay was a short delay, but the fact is you got hit by it in the required amount of time for it to matter, right? It doesn't matter how delayed it is if it doesn't have any place to go, okay? If you're going to finish, or you're going to terminate it in terms of realizing its energy potential. So you're going to realize its energy potential. It's when it does this, when it goes somewhere, and then it goes back again, and then it goes to the same damn place again, and then it goes back again, and then it goes to the same damn place. That's the part where energy has been absorbed out of the universe, okay? But it takes a while for that effect to make any difference to you personally. It's going to make a difference to the universe because a bunch of energy some of its energy has been lost, okay? But it's not going to matter to you if you get hit by it. So if the movement hits you, then it's going to be like it never got delayed. It doesn't matter whether it's 5 minutes late if it's still going to hit you. If it's 5 minutes late and that means you missed the appointment, then it's going to be gravity, okay? Because you would have been in a certain position, you would have been hit by it, but because it was late, you were in a new position and it just went this way. That's the idea. So you have to understand that it's if you take out the effects of the matter, that is, you make a special bubble that can withstand the insane chemical pressure that's going to exist inside the Earth, then yes, you're getting hit by less force because you've absorbed energy, and a magnet probably won't be as powerful. Yes, that would be the argument. Because you are absorbing the force, inside the Earth. But the point is how much it's going to absorb. It's a tiny, tiny fraction of the total energy of this external pressure. So you have to understand that this thing does suns. It does big, heavy, suns with 50 solar, 100, 200, 1,000 solar masses. I mean, gigantic objects still are absorbing more force, which means 99% of the force is just going right through, isn't affected. It's only a tiny fraction of the energy that's in the universe that's going to get absorbed inside the thickness of an Earth. So I'd say yes, it's there, but it's so fractional you're not going to notice it. But whatever. So there's nothing breaking the inverse square law. It still exists. It's just that the mathematics of doing this equation is so complicated, because technically you got matter, like I said, you got matter that was pushed this way, and it will create pressure this way, because the fact is there's too much pressure the other way. So it's like the water wave. It's an uncompressible substance that pops up. Okay, it goes in a direction that the force wasn't pushing it. Alright? And the same thing happens inside the Earth. So you're going to get hit, there's going to be a lot of misdirection. There's going to be a lot of energy absorbed this way that you're going to feel this way. And that's going to happen in all the 360 degrees. So it might all work out to the same thing, but the fact is that's what makes it a lot more complicated to calculate. But there's no threat to the inverse square law, in the sense that the inverse square law is just telling you there's a certain amount of energy coming off of a surface and it's equal in all directions. And that creates the inverse square law, because as you go out further, you only have so much energy that left, and now you're spreading it over a bigger and bigger circumference. That's the inverse square law. And that's true for waves or particles. Yeah, I think that's probably enough. I have to get rid of this. Okay. So now we'll do this speed of light crap video. No, I wanted to do the microwave, didn't I? Yes, I did. Alright, we'll put this back on. Alright. And let's see if we have a proper eraser. Alright. So as I have pointed out, photons are they have two features, and one of the features is just ignored. Now the frequency thing is everything, so that's all that I'm saying. Okay, it's a frequency. Now if you want to say because it has a frequency I can associate it as being wave-like or acting like a wave, you can say that, but I would say that's really stretching it. Okay, it's not a property. Like, it's like saying because we have eyes we are just like ladybugs because they have eyes. I mean, it's just a kind of a reach. So the fact that waves can have something in common with bowling balls or cannonballs or bullets doesn't mean anything. What they have in common is a function that should be appreciated in and of itself, independent of forcing it to be a certain kind of function. Oh, that's unfortunate again. That's my bad. I really should be able to get this stuff more consistent, but hey, life's tough. I mean, Linux is basically working. I want to make a pro Linux video, and every time I'm in the mood to do it, it does something really stupid, like wiping out all my hard drive space again. For just no in some error file, just 16 gigs just wiped out by an error file. Anyway, what the fuck? So anyway, where was I? All right, we're doing microwaves. All right, so the idea is the microwave oven's just a box, okay, and it's got a place where it's all coming out like light. It's a very bright light, and you can understand, just if it was a light bulb, you could understand if it was a very bright light and you were in a white room, a box, that the light would bounce certain ways more than it bounced other places. So there'd be lots of places where not too much light hit, and there'd be other places that would be really bright based on reflections, and how a light bounced around inside the box. Now the interesting thing is the holes. So they put a bunch of holes in the door, and what could that be for? Some of you I think do know, but anyway, Well, it's basically to break the take advantage of the fact that the light has a polarization. So again, none of this is being appreciated, but light when it's in space, it's nothing. It's just stuff, okay? And there's stuff in certain, you could look at the space and you could say, okay, I see 3 here. There's only 1 here. There's almost 2 there. You could see a pattern if you could actually see the stuff moving through space. You could see its pattern, all right? But you can't see it just, unfortunately, we can't see that pattern because it's such a tiny little pattern. It's happening so fast. But anyway, so it has polarization and then it has, the idea of the frequency. So there's 2 patterns really. There's a pattern this way that's got a frequency that has to be consistent. That's your lumps of your waves, okay? And then it has this polarization element that's telling you, if there were waves, it's telling you that they got to be this big, their size moving through space. And I would argue that that is fundamental to what a photon is in terms of how it's produced and how it's received. So on a surface, what's really got to happen, I don't know, I'll draw it as a flat plane. Okay, so just think of like a piece of paper. And what's happening with photons is they hit, okay, and so the first bit comes. So let's just say it's true that it's just a frequency. So it's just blobs of crap with a distance time between them, consistent distance. And they have this frequency thing. I would argue that the first bit hits right there. Okay, so it hits the piece of paper. It hits the substance. And what happens? Well, that atom gets fat, which makes the other atoms move or get fat, so to speak. So the fatness gets spread out by a couple of atoms. We could say 10 atoms, doesn't matter. Certain number of atoms will have to move because that atom moved. And then, now we have the time has happened, and the second bit hits, and it's going to hit somewhere, because of the polarization, distant from that object. It can't hit the same place, okay, because they're, in alignment. They're polarized this way, all right? So the frequency is here, and their polarization is going this way. And this, I've drawn it wrong in the sense that this distance is the same as this distance. So they're squished. Well, anyway, so the second one hits, and it hits a spot that is now moving this way. And it hits that spot. And that makes that spot, that part of that initial compression, all right? So this one got bigger, forced these out. It got energy, forced these out. Then these, as they're moving out, it gets hits again here, which means this one now has 2 elements of momentum. It had the first momentum, and now it has a second bump, okay? And so now this atom is really excited, okay? And then you could argue that then the third one hits, and it has to hit the same place, okay? Now we're talking about the distance has gone from the center to the second distance to now the third distance. You can sort of see. Now, it would be unlikely that this is true, that need a third one, right? Because the third one would have to coincidentally hit at the same vector, okay, the same direction as this second pulse. Because now we're really just saying that when this one gets excited, we'll have some more atoms moving out, but they won't be moving in that direction, they'll only be moving in this direction. But it could be that the third one has to hit one of these atoms moving in this direction, generally speaking. And it hits one of those, and that gives it enough energy to knock an electron free. Or you could say that's already electricity. So it's essentially creating an electric current by hitting something, moving it. Then another jolt comes in, hits it and moves it even faster, double speed. And then another jolt comes in and hits it again, okay, and gives it triple speed. And when it has triple speed, it's now electricity, because it's now moving an electron from one atom to the next. All right, and so that explains why polarization has to be proportional to frequency. If I have the right frequency, but I don't have the polarization right, then you can understand that when this bit is moving, I'll just erase that. Okay, so you hit this center thing, and now you're moving this energy out in these directions. Okay, in this direction, in this direction, in this direction, in this direction. If I hit it with the next piece of energy back here, that's not going to help push that. If I hit it up here, that's going to push in the wrong direction. So I'm really in trouble. So that's why the polarization, that is the distance from the first one, the distance this way, is going to be the distance that's going to be proportional to this amount of time. And so that's why the polarization is critical to the energy being able to hit at the right time for the speed of the atoms. That's why different atoms absorb different frequencies of light, is because of the speed at which the signal, the pressure, can move through the atoms. The bigger the atoms, you could argue, the slower. The smaller the atoms, the lighter, the easier it is to move them, okay, when you've caused the initial disturbance. So it's like saying heat. You heat this first one, that heats the rest of them, and it takes a certain time for the heat to transmit. And that is going to decide, your polarization is what's deciding how far this line goes. And the fact is, you got to hit behind it, not ahead of it, and you got to hit close behind it to add energy to it. Alright, so now this is draft. I haven't talked about this theory of light before, but it's I think it explains why polarization is so critical. So back to the microwave oven and the holes. So you could sort of understand that if the signal of the microwaves is big, okay, and that means the polarization, right? So my theory is that the microwaves are just, can't see that. All right. So I'm arguing that the polarization is large. For the microwave, it would be like 3 centimeters. All right, and you have a little hole. You know, let's just say it's a millimeter. Then all these little holes, you could sort of understand, are going to basically break a lot of the microwaves, right? Because one will go through this one and scatter that way, because we've got lots of surfaces, so there's lots of surfaces to make it go some other direction. And there's lots of this stuff to just absorb pieces of it. So you're breaking the microwaves, you know, over its polarization. Let's just say, clearly, if the polarization is this big compared to the holes, you can understand that no microwave goes through unbroken. So there's no possibility of a microwave getting through those holes without being broken. And the real question is there any angles or places where you could reconstruct them? Now, if you were right next to this surface, you're going to get some of these angles that might allow you to recreate the right polarization, that is the right height, and put it back in phase. But the odds are, at a distance, you're not going to have any chance of putting together enough of them. It's going to get fainter and fainter, and any microwave that actually is reconstructed at a distance is going to be very minor, very few of them. So, you know, like 1 in a million, or 1 in 100, or 1 in, you know, a tiny percentage of the microwaves on this side of the holes are going to be able to reconstruct in a form that can do you any damage at a distance, because you've just broken their polarization entirely. The phase is still okay for a lot of these pieces, okay? They're still they're still coming out at the right frequency. It's just that you've lost, you've broken it too much that there's now not enough bits to have a consistent frequency. This one's missing that bit, this one's missing that bit. So there's just not enough consistency, enough mass. And you've also spreading it because you're causing the fringes. You're spreading the microwaves over a larger area, which means even if you reconstruct the frequency, now your polarization is way too big. And so now when it hits a surface, it causes the effect, and then it hits way beyond where it's supposed to. It doesn't hit, to push the next, to give the electron the second jolt, the atom in the electron, the extra energy. It's hit way too far ahead of it. So it can't give it extra energy. It takes energy away rather than provides energy. All right, that's probably, that's enough for you to chew on. Yeah. So when you have a hole much smaller than the wavelength, the frequency that's going into the hole, that's really saying the frequency is telling you what the polarization is. So again, we're talking about the wrong thing being the critical factor. It's not the frequency that means the light's going to have a problem getting through the hole. It's the polarization that's proportional to the frequency that means any photon that was intact flying through space, and you put a smaller hole, it just isn't going to happen. Now, if you have a hole bigger than the frequency, bigger than the polarization, then you can get through it. You have some hope of keeping whole pieces intact. You didn't break the composite elements of the photon. Yeah. Good enough. All right, so we'll play some of this and just call it a day. Huffington Post. Exciting. I don't know if it has talking on it.
Everybody knows you don't have to be a chef to heat up food in a microwave. But did you know that you can also use these kitchen appliances to measure the speed of light?
You really can't, because the speed of light's already built into the function of frequency. Frequency has the speed of light in it already. So when you know the frequency, you already have to know the speed of light for it to mean anything.
Yes, we're talking about you, not a physicist. Let's explain the science first. Microwaves are part of the electromagnetic spectrum. They sit right between radio waves and infrared radiation.
So again, there's no waves ever demonstrated anywhere. There's no reason for you to think of it that way. There's a frequency. That's what makes this different from that, is frequency. That's it. That's the big one. The rest of this, they're just adding. I can draw it as particles just as well. There's absolutely no reason not to just recognize it's about frequency and polarization. Those are the two elements, those are the two real things that this spectrum is doing. Those are the real things this spectrum has. All this wave talk is just made up, superfluous.
Waves are characterized by their size or wavelength. And
so again, this wavelength will never show up. I never get a half a photon. You never get a quarter of a photon. You never get a piece of a wave. You never get any of this stuff. It's either there or not there, as Feynman points out. And it's true for the clumps as well. It's a binary system that carries any one of these mediums. So you can put analog crap on a binary signal. We do it all the time, okay? It's the signal, the carrier wave is always binary. It's always either on node, an off node, space. An on node, space, time, an on node. It's just a frequency between clumps of energy. That's it. That's all there's evidence for. Nothing else has, and there's no evidence of any sine wave having anything to do with any carrier wave in any signal. Again, you can put analog signals on top of the carrier, but the carrier is always just on and off.
Energy. Like all electromagnetic waves, microwaves oscillate as they travel through space.
No, they don't. There's no evidence of it. It's just made up. I can't stop people from saying it, but they don't have any evidence that anything's oscillating. That there's any positive and negative component. There's no negative component to any electromagnetic radiation. It has never made an object move towards it, ever. Okay, it's just not possible. It always applies momentum in the direction of the energy. Always, 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 always. Because it is in fact bullets. It's not some wave pulsating backward and forward.
You might think of one wavelength sort of like a jump rope being shaken up and down. You got it?
You can think of it a lot of stupid ways, and that's one of the stupid ways to think about it, because there's no evidence of this gradually on, gradually off energy. There's every bit of evidence. Again, and Feynman said it, and you people just, you'll sit there and tell me I have to believe in waves when you're God of your own theory. He's frankly God, right? He's the God of quantum mechanics, and he'll tell you it's not a wave. So why are you arguing with me?
When the microwaves oscillate, they heat the food in the places where the many jump ropes peak together, while the parts of...
Yes, obviously it heats them when the little bullets hit it. It causes effects to the electrons that they're hitting, causes them to move. And when they move, the whole atom eventually moves. That's heat.
The food where there are nodes, meaning the places where the jump ropes don't seem to move, stay cold. These nodes...
So it's kind of silly to say it that way, because that would have to, every single ray would have to be in perfect alignment for you to ever even detect that. And we know that that's not what's happening. It's firing this stuff all the time at all kinds of places.
Nodes occur at half wavelengths. And this is why microwaves come with that rotating tray.
Now, they come with a rotating tray because the microwaves are coming out of one side of the box, all right, and bouncing off the walls to hit the rest of the box, and it does that unevenly. So it makes perfectly good sense that if you move the food around, then you'll more evenly expose it to the light.
And why your food might heat up unevenly. But why are these waves particularly interesting? Because they move at the same speed as light does.
Yes, the same speed of all the forces. So again, another... I can't stop them, but this is like the plus and minus. We all know it's wrong, and it's frankly just wrong to talk about the speed of light. It's the speed of all the forces, okay? Magnetism travels the same speed. Electricity in a perfect environment, a near perfect conductor, travels the same speed. And gravity travels the same speed. So why are we talking about this as if light does it and the rest of the energy doesn't? No, all the energy does it, and light is just one form of this tiny bits of energy.
And we've got a handy equation to describe that. The speed of light equals frequency times wavelength.
Which is just retarded, right? It's like saying I'm, just feet times head, I don't know. They're the same thing. They're just a different, I could say period, and I use these different words for the same thing. And I can just create an inverse relationship. So we know frequency is dividing into, and the other one's dividing, the opposite, just changing the numerator and the denominator. And that's it. So they're reciprocals of each other. They're exact opposites of each other. So obviously when you cross multiply and cancel them out, you'll be left with the speed of light, because that's how you measure the frequency.
The term frequency refers to the rate at which an oscillation occurs that constitutes a wave.
Right. It talks about the period between the bits that matter, the humps. Yeah, but it's the period. It's the time between something.
Just imagine that jump rope and add a unit of time. We'll be measuring in hertz, or cycles per second. Finding the frequency is the easy part.
Yes, or lumps per second. See, it's that easy. There's just absolutely no reason not to just say, well, lumps per second works just as well.
It's usually listed on the label on the side or the back of your microwave. Ours is 2,450 megahertz, or
2.4 gigahertz.
2,450,000,000 hertz. To find the
2.4 gigahertz. Simpler.
wavelength, you'll need a few items from your pantry. You can use chocolate, or really any food that melts. To start, take out that rotating tray. We want our oscillating microwaves to hit the food at the same spots over and over again. Place your chocolate on a plate and cook it in the microwave on low heat. When the chocolate is slight...
Well, there is no low heat, so another trick to this whole thing is that just means you're turning it on, turning it off. Microwaves only come out one way, a lot. And so all they do is turn the gun on and off. They just turn the light on and then let it, oh, it's getting too hot, turn it off. Wait a while, turn it back on. I mean, there is no low setting.
melted, take the plate out of the microwave. See those spots? Grab a metric ruler and measure the distance between them in centimeters. That's half the wavelength of the microwaves that the oven produces. Double that distance and you'll have the wavelength of the waves emitted by the microwave.
Right, and you can draw straight lines to explain why there's more at certain distances. So again, it's just not a big surprise. And that sort of even more directly proves the clump theory, right? Because you're basically just saying, look at the distance between the clumps. Look at the distance between the clumps.
Plug the frequency and the wavelength into the formula and calculate. This number should be pretty close to the speed of light, which is about 29,400,000,000 centimeters per second, or 294.
Right. So you could do the same thing by just sitting there making the holes in the door bigger and bigger until you get microwaves coming out, unmolested ones, right on the surface. And that'll tell you the same thing. It'll tell you exactly what the frequency is. And once you know the frequency, yes, the speed of light's already in the description of how we measure frequency. It's already the constant deciding what the word hertz means.
Million meters per second. Even if your friends don't want to eat these microwave dishes, at the very least you'll impress them with your science skills.
Right. So anyway, crappy vernacular at any rate. I mean, I'm not saying this isn't true. I'm just saying, obviously it can be explained by drawing rays and showing how the rays bounce inside the box. And so it's just completely not dependent. You're not required to believe in wave theory to believe microwave ovens work. So I don't know what this one is, but I guess it's the same damn thing, right? How a microwave oven works. We already know that. So this is telling you 6.4 centimeters is telling you essentially that the polarization is also 6.4 centimeters. So a hole, 6.4 centimeters, okay, then you're going to start getting a lot of microwaves coming out. But up to that size, you can make lots of different size holes. See, they could put smaller holes, they could put bigger holes. Now, I guess if they put bigger holes, people would get afraid, because they look too big, But obviously, the smaller the hole, we know, the more it diffracts the light, the more it spreads it. So smaller holes would be better because it's going to really mess it up more than bigger holes. Yeah. Alright, so we really don't need to play this, right? It's going to be terribly redundant, no doubt. Now let's just play some of it.
This microwave oven is a truly remarkable feat of engineering. The rapid heating that makes microwaves popular is made possible by power provided from this vacuum tube. Now, if you picture a vacuum tube at all, it's likely in a radio like this. Inevitably, tiny transistors and microchips replace clunky vacuum tubes, but it's too soon to relegate them to the museum. Microchips can't easily replace tubes for producing power, for example, in heating food. Now, a microwave contains three main components. A vacuum tube.
Just saying that the vacuum tube is really just just explaining how to create the higher frequency stuff. You do it more efficiently, okay, with a tube that you create this elemental heating.
Tube called a magnetron. It generates the energy that heats food. A waveguide hidden in the wall to direct that energy to the food, and a chamber to hold the food and safely contain the microwave radiation.
Okay, don't mean.
In principle, a microwave oven heats no differently than any other type of heat transfer. At a molecular level, heat is a transfer of energy that results in increased motion of the molecules.
Right, but it has to be, this is the whole key to the microwave, is the convenient thing where it's basically the size of water molecules is what makes it work. If water wasn't heated by a microwave, it wouldn't be very useful. I mean, if it wasn't for the size of water molecules, we wouldn't bother with microwaves to do heating because it wouldn't work very well. It doesn't heat anything else very well.
Of the substance. Since we aren't quantum-sized, we observe this increase in motion as a rise in temperature. In a traditional oven or stove, we heat food by placing a pan on a burner, or in the oven where the walls radiate heat, which cooks the outside of the food. The inside's cooked when heat transfers from the surface of the food to its interior. In contrast, energy from the magnetron penetrates into the food, which means the whole mass of the food can be cooked simultaneously.
Right, because you're basically cooking it with gravity. You're cooking it with a force rather than cooking it by obliging a bunch of atoms to jiggle. You have to have air in your oven or your oven won't work, right? In a vacuum, it's not going to get hot.
How does it do this? Well, our food is filled with water, which is positively charged at one end and negative at the other. To give these molecules more energy, we expose it to electromagnetic waves that emanate from the tube. By definition, the waves have electrical and magnetic fields that change direction rapidly.
Oh, they really don't do any of that by definition, and certainly not by experiment, and certainly not by any evidence, and all of that stuff. All there's evidence for is that it carries energy, and obviously, if if I'm shooting a gun, it's all about how many bullets hit you, right? So obviously, a higher frequency, as I pull the trigger more often, you're going to be more dead or more likely to be dead, right? I mean, any idiot can figure out that if they're going to be shot by somebody, they'd rather it be a six-shooter than a machine gun. I mean, duh.
For this oven, the direction of the fields change 2.45 billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the hydrogen bonds between neighboring water molecules.
The point is that you're hitting it in resonance. So the only reason why the water molecule can, it becomes like a pendulum, and you keep adding energy as it tries to reorient itself. So you just keep hitting it, and if you've got off frequency, then it's not going to be able to add energy. You're going to do exactly what I was saying before. You're going to hit in front of it and then oblige the electron to move the opposite direction. So it's the size of the molecules that the whole thing is really based on, blah, 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 blah.
Now, you can get an idea of the wavelength of the energy emitted from the magnetron using cheese.
So it's the same frickin' video.
Now, you can see on here sections where the cheese is completely melted and other sections where it's completely unheated. The oven's metal walls only reflect waves of a length that fits inside the oven. This standing wave causes hot and cold spots inside the oven. The three-dimensional pattern of waves is difficult to predict, but the principle can be seen by looking at the waves in a single dimension. The peaks and valleys in the wave represent the greatest energy of the wave. Well, the nodes here correspond to the cold spots inside the chamber.
Right, so again, particle theory, this works just as well. So it's just this isn't an argument about anything unique about waves. It's just saying something about frequency. I mean, it's about the nodes, as I've called them also. And that's all that matters, is the nodes and the distance of the nodes. It doesn't matter whether you think the nodes are just red bullets or whether you think the nodes are doing this wobbly thing. And again, if you were going to draw the nodes correctly, you would draw them, out of perfect alignment, because that would represent its frequency. So the distance between the nodes would be the frequency within which all the nodes fit. But they're a little bit out of alignment, and that's, you have to have it. Those two things have to be proportional for the energy to be received as a photon. That is, for the energy to cause electricity, and that's how we measure it. That's how we measure it. Obviously, food can measure it differently. Okay, but when we're trying to measure it, we have to make it cause an electric current. Alright, so that's probably enough. I believe it is. Oh, okay, good. Then we're in agreement. Alright, so whatever. Till the next time. When I probably will just be responding to useless, snarky crap that, just doesn't serve much of a purpose. Because no one's going to make any rational arguments or provide any evidence of anything that means anything. And such. So forth and what, they'll just stick with their old religious ideas because they don't want to, they've had their picture of Jesus on the wall for a long time, and they want to change the picture because the size of the picture won't match, and you'll be able to see the old dirt marks or something. Some trivial reason why they're afraid to change. Yeah. But whatever.